Welcome to a journey through the most overlooked chapter in the history of our planet. You know about the dinosaurs, you have heard of the Ice Age. But what happened in between? For millions of years after the asteroid struck and the dinosaurs vanished, Earth transformed in ways that would seem like science fiction if we did not have the fossils to prove it. Giant snakes longer than buses slithered through swampy forests. Whales with legs walked on beaches before returning to the sea. Antarctica was covered in green forests instead of ice. Horses were no bigger than house cats. This forgotten age shaped everything about the world we live in today, including the evolution of our own ancestors. So settle in, get comfortable, and let your mind drift back 66 million years to the day the old world ended and a strange new one began. Close your eyes and imagine a planet being reborn, where the rules of life were being rewritten, and where the ancestors of every mammal alive today were taking their first steps into an empty world full of possibilities. This is their story, this is our story, and it all begins with fire falling from the sky. Chapter 1. The day the world changed. 66 million years ago, the sky above what we now call the Yucatan Peninsula blazed with an impossible light. A rock from the depths of space, measuring 10 kilometers across, tore through the atmosphere at 20 kilometers per second. The impact released energy equivalent to 10 billion atomic bombs, creating a crater 150 kilometers wide. The ground melted instantly, turning to liquid rock that splashed upward like water from a stone thrown into a pond. A wall of superheated debris shot into the upper atmosphere, reaching all the way to space itself. Earthquakes measuring beyond any scale we can imagine rippled across the entire planet within minutes. Tsunamis taller than skyscrapers raced across ancient oceans, scouring coastlines bare of life. The dinosaurs, who had ruled Earth for 165 million years, would not see another sunrise. Flying reptiles fell from darkening skies. Marine reptiles thrashed in boiling seas. The great herds of Triceratops and the fearsome Tyrannosaurus rex faced their final hours. Within days, 3/4 of all species on Earth began their march toward extinction. The Cretaceous period, an age of giants and endless summers, came to an abrupt and violent end. But this catastrophe was not the end of the story. It was, in fact, a beginning. The empty world that remained would give rise to an age we have largely forgotten, an era that would eventually lead to our own existence. Chapter 2. Nuclear winter descends. The darkness that followed the impact was unlike anything the planet had experienced in hundreds of millions of years. Trillions of tons of pulverized rock, soot, and sulfur compounds hung suspended in the stratosphere, forming a thick blanket that blocked out the sun. Temperatures plummeted as this veil of destruction reflected precious sunlight back into space. Within weeks, global temperatures dropped by as much as 28 degrees Celsius in some regions. The warmth that had characterized the Cretaceous world vanished, replaced by freezing conditions that reached even the tropical zones near the equator. Plants, deprived of sunlight, could not perform photosynthesis. Forests that had stood for millions of years withered and died. The great ferns and cycads turned brown and crumbled. Without plants, the herbivores starved. Without herbivores, the carnivores followed them into extinction. This nuclear winter lasted for months, perhaps even years. Snow fell in places that had never known ice. Rivers froze solid. The oceans, once teeming with life, became cold and acidic as sulfuric acid rain fell continuously from the poisoned sky. Those creatures that had survived the initial impact now faced a world transformed into a frozen wasteland. Food chains collapsed from the bottom up. Yet somehow, in burrows beneath the frozen ground, in caves deep within mountains, and in the darkest depths of the ocean, life persisted. Small creatures, warm-blooded and adaptable, waited in the darkness. They did not know it, but they were the future. Chapter 3. The survivors emerge. When the skies finally began to clear, perhaps 2 or 3 years after the impact, the survivors cautiously emerged into a transformed world. These were not the giants of the Cretaceous. They were small, mostly nocturnal creatures that had lived in the shadows of the dinosaurs. Mammals, no larger than rats, crept from their burrows, blinking in the dim light. These animals had advantages that the dinosaurs lacked. Their warm-blooded metabolism allowed them to maintain body temperature in the cold. Their fur provided insulation. Many had been omnivores or insectivores, able to survive on seeds, roots, insects, and carrion when other food sources vanished. Birds, the descendants of dinosaurs themselves, also survived. Small-bodied species that could shelter in whatever vegetation remained had made it through. Crocodiles and turtles, able to slow their metabolisms and go months without food, emerged from rivers and swamps. Lizards and snakes, hidden in underground refuges, also persisted. In the oceans, sharks continued their ancient lineage. Even some plants had survived, their seeds lying dormant in the soil, waiting for the right conditions to germinate once more. The survivors shared common traits. They were small, adaptable, and able to exploit limited resources. They could reproduce quickly when conditions improved. Most importantly, they were generalists rather than specialists, able to eat many different foods and live in various environments. These humble creatures, unremarkable by Cretaceous standards, would inherit an empty planet. The age of dinosaurs had ended. The age of mammals was about to begin. Chapter 4. A world of ash and silence. The early Paleocene world, beginning 66 million years ago, was a place of eerie stillness. Where once the earth had thundered with the footsteps of giants, now there was silence. The landscapes were grey and barren, covered in layers of ash and impact debris that would take thousands of years to erode away. The forests that had once covered much of the planet were gone, replaced by wastelands of dead trees and bare soil. Without large animals to disturb the undergrowth, without the calls of pterosaurs overhead, without the bellowing of huge sauropods, the world seemed empty and lifeless. Rivers ran thick with sediment, their courses changed by the chaos of the impact. Lakes filled with ash, their waters murky and acidic. The oceans too were changed. The great marine reptiles were gone. The ammonites, spiral-shelled creatures that had thrived for hundreds of millions of years, had vanished entirely. Coral reefs, once vibrant ecosystems, lay dead and bleached. The food webs that had sustained oceanic life for eons had collapsed. Yet in this apparent desolation, change was stirring. Bacteria and fungi broke down the vast quantities of dead organic matter, recycling nutrients back into the soil. Hardy fern spores blown on the wind began to take root in the ash. Within a few thousand years, a carpet of ferns covered much of the land, the first stage in ecological recovery. These simple plants prepared the soil for what would come next. Life, suppressed but not defeated, was beginning its slow comeback. Chapter 5. The first green shoots. 10,000 years after the impact, the planet was showing signs of recovery. The fern prairies that had initially colonized the devastated landscapes were gradually being replaced by more complex plant communities. Seeds that had lain dormant in the soil, protected from the worst of the catastrophe, began to sprout. Flowering plants which had evolved during the Cretaceous proved remarkably resilient. These angiosperms had advantages over more primitive plants. They could reproduce quickly, their flowers attracting what few pollinating insects had survived. Their seeds were often protected in fruits or hard shells, allowing them to endure harsh conditions. Slowly, forests began to regrow, though they were different from those that had existed before. The new forests were dominated by different species, ones that could thrive in the altered climate and soil conditions. Palms spread across tropical regions. Deciduous trees, able to shed their leaves and conserve energy during difficult seasons, flourished in temperate zones. Conifers maintained their presence, particularly in cooler regions. With the return of plant life came the return of herbivorous animals. Insects, which had survived better than many other groups, pollinated the flowers and fed on the leaves. Small mammals, emerging from their hiding places, found abundant food once more. Their populations began to grow. Within 100,000 years of the impact, ecosystems were functioning again, though they were simpler and less diverse than those of the Cretaceous. The planet was healing. Green was returning to a world that had been grey and brown. The stage was being set for the next chapter in the history of life. Chapter 6. Tiny Ancestors Awaken. The mammals that survived the extinction were remarkably small by modern standards. Most weighed less than 1 kilogram, no larger than a modern squirrel or rat. During the age of dinosaurs, mammals had been relegated to the margins, forced to remain small to avoid competing with the dominant reptiles. They were mostly nocturnal, scurrying through the undergrowth at night to avoid being eaten by theropod dinosaurs. But now, with the dinosaurs gone, a world of opportunity opened before them. These early Paleocene mammals began to diversify at an astonishing rate. Within just a few million years, they evolved into forms adapted to every available ecological niche. Some remained small and insect-eating, similar to modern shrews. Others grew larger and began to eat plants. Still others became predators, hunting their fellow mammals. Without large reptilian competitors, there was nothing to stop mammals from experimenting with new body plans and lifestyles. Among these early mammals were the ancestors of nearly all modern mammal groups. Small tree-dwelling creatures would eventually give rise to primates, the group that includes monkeys, apes, and humans. Others would evolve into the ancestors of horses, whales, bats, and elephants. The fossil record from this time shows an explosion of new species, each adapting to fill the empty niches left by the dinosaurs. These animals had fur to keep them warm, allowing them to remain active in cooler climates and at night. They nursed their young with milk, giving their offspring a better chance of survival than egg-laying reptiles. Their relatively large brains made them adaptable and capable of learning. These advantages would serve mammals well in the changing world of the Paleocene. Chapter 7. The Age of Weird Mammals. The mammals of the early Paleocene were unlike anything alive today. Evolution, working rapidly to fill empty ecological niches, produced creatures that seem bizarre to our modern eyes. Without the constraints imposed by dinosaur competition, mammals experimented with body forms that would later prove unsuccessful, but flourished for a time in this transitional world. Leptictidium, a small insect eater, hopped on its long hind legs like a miniature kangaroo. Criacus, an early ungulate ancestor, looked more like a weasel than any modern hoofed animal. Pantolambda, one of the first large herbivorous mammals, had a bulky body and short legs, weighing perhaps 90 kilograms. Purgatorius, one of our own earliest primate ancestors, was a tiny tree dweller that looked more like a squirrel than anything we would recognize as a primate. These transitional forms reveal evolution in action, showing how mammals groped their way towards successful body plans through trial and error. Many lineages that flourished in the Paleocene would later go extinct, replaced by more efficient designs. The condylarths, early hoofed mammals, gave rise to more specialized groups before dying out themselves. The multituberculates, rodent-like mammals that had thrived even during the dinosaur age, began their long decline. Strange carnivorous mammals called mesonychids appeared, with hooves instead of claws, a design that would ultimately prove less effective than the retractable claws of modern carnivores. This era of experimentation lasted for millions of years, as mammals tried out different strategies for survival. It was a time of rapid change and incredible diversity, a creative explosion of life that would eventually lead to the more familiar forms we know today. Chapter 8: Titanoboa's Realm. Not all of the giant animals in the post-dinosaur world were mammals. In the hot, humid forests of South America, approximately 60 million years ago, an enormous reptile ruled the swamps and rivers. Titanoboa, the largest snake ever to exist, grew to lengths of 13 meters and weighed over 1,000 kilograms. This massive predator was as long as a school bus and as thick as a human waist at its widest point. Titanoboa lived in a world very different from our own. Global temperatures were much higher, with tropical regions experiencing average temperatures of 30 to 34 degrees Celsius. These hot conditions were essential for Titanoboa, as reptiles depend on environmental heat to regulate their body temperature. The warmer the environment, the larger a cold-blooded animal can grow. The snake inhabited the vast coal swamps of what is now Colombia, where it hunted in murky waters for crocodilians, large fish, and any other animals unfortunate enough to cross its path. Like modern anacondas, Titanoboa was likely a constrictor, wrapping its enormous body around prey and squeezing until the victim suffocated. The existence of such a massive reptile tells us much about the Paleocene world. The climate must have been consistently hot and humid to support such a creature. Food must have been abundant to sustain its enormous bulk. And perhaps most significantly, there were not yet mammalian predators large or powerful enough to threaten such a beast. Titanoboa represents the last gasp of reptilian dominance on land. Within a few million years, mammals would evolve into forms large and diverse enough to outcompete such giant reptiles. But for a brief moment in geological time, the age of giant reptiles had one final chapter. Chapter 9. The first primates appear. High in the trees of Paleocene forests, a revolution was taking place that would eventually lead to the evolution of humans. The first true primates appeared approximately 55 to 60 million years ago, during the transition from the Paleocene to the Eocene epoch. These early primates were small, perhaps the size of a mouse or small squirrel, and looked quite different from modern monkeys or apes. They had grasping hands with opposable digits, allowing them to grip branches securely as they moved through the canopy. Their eyes began to move forward on their skulls, providing binocular vision that allowed them to judge distances accurately when leaping between branches. This was crucial for animals living in a three-dimensional environment where a misjudged jump could mean death. The early primates also had relatively large brains compared to their body size, a trend that would continue and accelerate throughout primate evolution. These larger brains helped them process complex visual information, remember the locations of food sources, and navigate the intricate maze of forest branches. Unlike many mammals, primates relied more on vision than smell, a shift that would have profound implications for brain development. They also tended to have smaller litters and invest more time in caring for their offspring, strategies that increased the survival rate of their young. The forests of the early Cenozoic were ideal habitats for these creatures. Abundant fruits, flowers, and insects provided food. The warm climate allowed forests to spread across much of the planet. In these treetop worlds, primates diversified and flourished, developing the characteristics that would eventually lead to monkeys, apes, and finally, humans. Our story as a lineage begins in these ancient forests. Chapter 10: Forests Return to Life. By 10 million years after the extinction, roughly 56 million years ago, forests had returned across much of the planet. These were not the same forests that had existed during the Cretaceous, but entirely new ecosystems adapted to the changed world. The trees were primarily flowering plants rather than the conifers and cycads that had dominated before. These angiosperm forests were denser and more productive, supporting a greater diversity of animal life. In tropical regions, rainforests developed that were even more extensive than those of today. Where now we find the Amazon, vast forests stretched even further. Palms and broadleaf trees created thick canopies that blocked out much of the sunlight, creating dim, humid understories where ferns and shade-loving plants thrived. Vines and lianas tangled through the branches. The forests rang with the calls of birds and the buzzing of countless insects. In temperate zones, deciduous forests spread across the continents. These trees, which shed their leaves seasonally, had advantages in regions with varying conditions throughout the year. Oaks, maples, and other familiar tree families were establishing themselves, though many of the specific species would not evolve for millions of years yet. Even near the poles, where today we find ice and tundra, forests grew. Antarctica and the Arctic regions were warm enough to support temperate forests, with trees growing almost to the poles themselves. This was a world without permanent ice caps, where the climate was warmer and more equitable across latitudes. The return of forests transformed the planet. Trees stabilized soil, regulated water cycles, and moderated temperatures. They provided habitat for countless species. The recovery of forest ecosystems marked the full healing of the planet from the catastrophe that had ended the dinosaur age. Chapter 11: The Greenhouse Earth. Approximately 56 million years ago, Earth experienced one of the most rapid and extreme warming events in its history. This event, called the Paleocene-Eocene thermal maximum, marked the beginning of the Eocene epoch and created a greenhouse world unlike anything humans have experienced. Global temperatures rose by 5 to 8 degrees Celsius in just a few thousand years, an incredibly rapid change in geological terms. The causes of this warming are still debated by scientists, but the most likely explanation involves the massive release of carbon dioxide and methane into the atmosphere. Volcanic activity may have released carbon from underground reservoirs. Methane trapped in ocean sediments may have been released as the oceans warmed, creating a feedback loop that accelerated warming. Whatever the cause, the effects were dramatic. The Arctic Ocean, which today is covered by ice, had water temperatures of 23 degrees Celsius, similar to modern subtropical seas. Crocodilians, which today live only in warm regions, swam in Arctic waters. Palm trees and tropical plants grew on the shores of what is now Alaska and northern Canada. Antarctica, while separated from other continents, was ice-free and covered in temperate forests. In the tropics, temperatures may have exceeded 40 degrees Celsius, pushing the limits of what many organisms could tolerate. Rainfall patterns shifted dramatically. Some regions that had been relatively dry became wetter. The increased warmth drove intense evaporation from the oceans, leading to more vigorous weather systems. Storms became more powerful. This greenhouse world lasted for approximately 200,000 years before temperatures gradually declined. But during this hot phase, life adapted and even flourished, with mammals diversifying rapidly and spreading to every continent. Chapter 12: Dawn Horses and Ancient Whales. The Eocene epoch, spanning from 56 to 34 million years ago, witnessed the emergence of early forms of many modern mammal groups. Among the most remarkable were the ancestors of horses and whales, animals that would undergo dramatic transformations from their Eocene beginnings. Eohippus, also known as Hyracotherium, was the dawn horse, standing only 35 to 50 centimeters tall at the shoulder. This tiny animal looked more like a small dog than a modern horse. It had 4 toes on its front feet and 3 on its back feet, each ending in a small hoof. It lived in forests rather than grasslands, browsing on soft leaves and fruits rather than grazing on tough grasses. Its teeth were low-crowned and suited for soft vegetation. Over millions of years, this small creature would evolve into the large, single-toed horses we know today, a transformation driven by changing environments and the spread of grasslands. Even more remarkable was the evolution of whales. In the early Eocene, approximately 50 million years ago, the ancestors of whales were still land animals. Pachycetus, one of the earliest whale ancestors, looked like a large dog or wolf and lived near rivers and coasts. It hunted fish in shallow water, but still walked on land. Over just 10 million years, these animals would transition completely to aquatic life. Ambulocetus, appearing around 49 million years ago, could both walk and swim, with powerful legs and a long tail. Dorudon, by 40 million years ago, was fully aquatic, with a streamlined body and flukes for swimming. This rapid transition from land to sea represents one of the most dramatic evolutionary transformations in the history of life. Chapter 13. The Pétième Crisis. The Paleocene-Eocene thermal maximum was not just a period of warmth, it was also a time of ecological crisis that tested the resilience of life on Earth. The rapid warming caused significant extinctions, particularly in the oceans. Deep-sea organisms adapted to cold, stable conditions suffered greatly. Many species of foraminifera, tiny shell-forming protists that are crucial parts of marine food webs, went extinct. The extinction rate among these organisms was between 35 and 50%, a significant loss. The oceans became more acidic as they absorbed vast quantities of carbon dioxide from the atmosphere. This acidification made it difficult for organisms with calcium carbonate shells to build and maintain their protective structures. Coral reefs, which had been recovering from the end Cretaceous extinction, suffered another setback. On land, mammals experienced significant changes. Many of the archaic mammal groups that had flourished in the Paleocene went extinct or declined dramatically. In their place, modern mammal orders underwent rapid diversification and expansion. Primates, which had been small and relatively rare, spread and diversified. The ancestors of horses, rhinoceroses, and tapirs appeared. Early relatives of elephants emerged. This turnover suggests that the rapid warming created new ecological opportunities for those animals that could adapt quickly. The PETM also triggered massive migrations. As temperatures rose, many species moved toward the poles seeking cooler conditions. Land bridges, exposed by lower sea levels in some regions, allowed animals to move between continents. This movement and mixing of previously separated faunas led to increased competition and further changes in community structure. The crisis lasted approximately 200,000 years before conditions gradually returned to normal, but the biological legacy of this event would persist for millions of years. Chapter 14. Tropical Antarctica. During the Eocene epoch, Antarctica was utterly unrecognizable compared to the frozen continent we know today. Positioned over the South Pole but not yet covered in ice, Antarctica enjoyed a temperate climate similar to modern-day Tasmania or southern New Zealand. Forests covered the land from the coasts to the interior. These were not tropical rainforests, but rather cool, temperate forests dominated by southern beech trees, podocarps, and tree ferns. In sheltered valleys and along the coasts, palms and other more warmth-loving plants grew, suggesting that even in winter, temperatures remained relatively mild. The continent supported a rich diversity of animals. Marsupials, which today are found mainly in Australia, and the Americas, lived in Antarctic forests. Small mammals scurried through the undergrowth. Birds filled the skies, including early penguins that could still fly and were much larger than their modern descendants. In the surrounding seas, primitive whales and other marine mammals hunted for fish. The ocean temperatures around Antarctica were perhaps 15 to 20 degrees Celsius, far warmer than the freezing waters of today. This warm Antarctic was possible because of the global climate and ocean currents of the time. The continent was still connected to South America by a land bridge, preventing the development of the Antarctic circumpolar current that today isolates the continent and keeps it frozen. Warm ocean currents from the tropics reached Antarctic shores, moderating the climate. The atmospheric carbon dioxide concentration was much higher than today, creating a powerful greenhouse effect. Eventually, around 34 million years ago, Antarctica would separate from South America, allowing the circumpolar current to develop. The continent would cool rapidly, and ice sheets would begin their inexorable advance, burying these ancient forests forever. Chapter 15. The Diversification Explosion. By the Middle Eocene, approximately 40 million years ago, mammals had achieved a level of diversity that rivaled or exceeded that of any other time in their history. Nearly all modern mammal orders had appeared, and they had diversified into countless species occupying every available ecological niche. In the oceans, whales had completed their transition from land to water and had divided into two major groups. The toothed whales, ancestors of dolphins and sperm whales, were active predators hunting fish and squid. The baleen whales, though not yet possessing the filtering structures they would later develop, were beginning to exploit different food sources. Seals and sea lions, descended from bear-like ancestors, were also beginning their transition to marine life. On land, the diversity was even more impressive. Bats, the only mammals capable of true powered flight, had appeared and diversified into insect eaters and fruit eaters. Rodents, which would eventually become the most diverse mammal order, were spreading and adapting to countless ecological roles. The first rabbits appeared with their distinctive hopping locomotion and specialized teeth for eating tough plant material. Carnivorous mammals had split into two major groups. The carnivorans, including the ancestors of dogs, cats, bears, and weasels, were becoming more sophisticated predators. The creodonts, now extinct, were their competitors. Large herbivores included early relatives of elephants, horses, rhinoceroses, and hippos. In South America and Australia, isolated from other continents, unique mammal faunas evolved independently. This explosion of diversity transformed ecosystems. Food webs became more complex, with multiple layers of predators and herbivores. Mammals had truly inherited the Earth, occupying every role from tiny insect eaters to massive herbivores and fearsome predators. The age of mammals had reached its peak. Chapter 16, Giants of the Forest. The Oligocene epoch, beginning 34 million years ago, saw the evolution of some of the largest land mammals ever to walk the Earth. Among the most impressive was Paraceratherium, also known as Indricotherium, a creature that dwarfed modern elephants. Standing 5.5 meters tall at the shoulder and measuring 8 meters in length, this animal weighed approximately 15 to 20 tons. It was the largest land mammal that has ever existed. Paraceratherium belonged to the rhinoceros family, though it looked quite different from modern rhinos. It had no horn, and its long neck allowed it to browse on leaves high in the trees, similar to modern giraffes. Its massive legs were like tree trunks, necessary to support its enormous weight. This giant lived in the forests and woodlands of Asia, from what is now Pakistan to Mongolia. The climate was still relatively warm, though cooling compared to the Eocene, and vegetation was abundant enough to support such massive herbivores. Other giant mammals shared this world. Brontotheres, distant relatives of horses and rhinoceroses, also reached enormous sizes, with some species weighing over 2 tons and bearing elaborate horns on their snouts. Entelodonts, sometimes called hell pigs, were massive omnivorous mammals that could weigh up to 500 kilograms, with huge heads and powerful jaws. These giants represent an important principle in mammal evolution. When food is abundant and competition is manageable, natural selection often favors larger body sizes. Larger animals can defend themselves better, access food sources unavailable to smaller creatures, and maintain more stable body temperatures. However, gigantism also has costs, requiring vast amounts of food and making animals vulnerable to environmental changes. Chapter 17. The first grasses. Around 35 to 40 million years ago, a seemingly insignificant plant began to spread across the planet, a plant that would transform ecosystems and drive the evolution of countless animal species. Grasses, which had existed in some form since the late Cretaceous, began to expand dramatically during the Oligocene and especially the Miocene epochs. These plants had several advantages that allowed them to outcompete other vegetation in certain environments. Grasses grow from the base rather than the tip, meaning they can survive being eaten or cut and quickly regrow. Their roots form dense mats that hold soil together, preventing erosion. They can survive in drier conditions than many trees and shrubs, requiring less water to thrive. Perhaps most importantly, grasses could tolerate fire, an increasingly common occurrence as the climate dried. When forests burned, grasses were often the first plants to return, gradually converting woodlands into grasslands. The spread of grasslands created entirely new ecological opportunities. Open plains replaced forests across large areas of every continent except Antarctica. These grasslands could support vast herds of grazing animals in a way that forests could not. The abundance of grass created an abundant food source, but it was a challenging one. Grass contains silica, a mineral that wears down teeth rapidly. Only animals with specialized dentition could exploit this resource effectively. This led to evolutionary innovations among herbivorous mammals. Horses evolved taller teeth with complex ridges. Bovids, the family that includes cattle, antelopes, and goats, developed continuously growing teeth. Elephants evolved a remarkable system where new teeth move forward in the jaw to replace worn ones, giving them 6 sets of teeth throughout their lives. Chapter 18, Terror, Birds Rise. While mammals dominated most of the world during the Cenozoic era, in South America, an entirely different group of predators held sway. The Phorus racids, better known as terror birds, were enormous flightless birds that ruled the continent for millions of years. These creatures stood up to 3 meters tall and could weigh up to 400 kilograms. Their most striking feature was their massive head, up to 60 centimeters long, with a huge hooked beak capable of crushing bones and tearing flesh. Unlike the small brains of their dinosaur ancestors, terror birds had relatively large brains and were likely quite intelligent predators. South America during the Oligocene and Miocene was isolated from other continents, an island continent where evolution followed a unique path. Without large mammalian carnivores like cats or dogs, birds evolved to fill the predator niche. Terror birds were the apex predators, hunting the various mammals that inhabited South American grasslands and forests. They could not fly, but they did not need to. Their powerful legs allowed them to run at speeds perhaps exceeding 50 kilometers per hour, fast enough to chase down most prey. Their hunting strategy likely involved using their massive beaks to strike prey with devastating force, either killing it outright or stunning it before tearing it apart. Some species may have hunted in groups cooperating to bring down larger prey. These birds survived for over 60 million years, from shortly after the dinosaur extinction until about 2.5 million years ago. Their reign finally ended when South America connected to North America, allowing mammalian predators like jaguars and saber-toothed cats to invade. Unable to compete with these sophisticated carnivores, the terror birds gradually went extinct, leaving behind only fossils to remind us of this remarkable experiment in bird evolution. Chapter 19. Ancient elephants and their kin. The elephant family, known scientifically as Proboscidia, has a long and fascinating evolutionary history that began in Africa around 60 million years ago. The earliest members of this group were small, pig-sized animals that looked nothing like modern elephants. Phosphotherium, one of the oldest known proboscideans, lived in North Africa during the Paleocene and weighed only 15 kilograms. It had no trunk, just a slightly elongated snout. Over millions of years, this lineage would evolve into the enormous, intelligent animals we know today. By the Oligocene and Miocene epochs, proboscideans had diversified remarkably. Merytherium, living around 37 million years ago, was about the size of a tapir and semi-aquatic, spending much of its time in rivers and swamps. It had a flexible upper lip and small tusks, hints of features that would become more pronounced in later species. Dinosaurs were strange elephants with downward curving tusks in the lower jaw rather than the upper, possibly used for digging roots or stripping bark. Gomphotheres had 4 tusks, 2 in the upper jaw and 2 in the lower, and spread across most of the world. Mastodons, which would survive until just 10,000 years ago, had cone-shaped teeth for browsing on leaves and branches. The evolution of the trunk was one of the most remarkable developments. This flexible, muscular organ is actually a fusion of the nose and upper lip, containing over 40,000 individual muscles. It allows elephants to manipulate objects with great precision, strip leaves from branches, drink water, communicate through touch, and perform countless other functions. The trunk evolved gradually over millions of years, becoming longer and more versatile with each generation, driven by the advantages it provided in feeding and survival. Chapter 20. The Grande Coupure. Approximately 33.5 million years ago, European ecosystems experienced a dramatic and sudden change known as the Grande Coupure, which means the Great Cut in French. This event marked the boundary between the Eocene and Oligocene epochs and resulted in a major turnover of mammal species across Europe. Many of the endemic European mammal families that had evolved in isolation went extinct or disappeared from the fossil record. In their place, Asian mammal species invaded, fundamentally changing the character of European faunas. The cause of the Grande Coupure was likely a combination of climate change and geographic factors. Global temperatures were dropping as Antarctica became isolated and began to accumulate ice. This cooling made northern latitudes less hospitable for many warm-adapted species. At the same time, sea levels dropped, exposing land bridges between Asia and Europe that had previously been submerged. This allowed Asian mammals, which had evolved in a more competitive environment, to migrate westward into Europe. The Asian immigrants included early rhinoceroses, anthracotheres, which were hippo-like animals, various rodents, and new types of carnivores. These animals were generally more advanced and efficient than their European counterparts, having evolved alongside a greater diversity of competitors in Asia. The European endemics, isolated for millions of years, could not compete effectively and were driven to extinction. This event illustrates an important principle in evolutionary biology. Isolated populations may thrive in their limited environment, but become vulnerable when exposed to competition from species that evolved under more challenging conditions. The Grande Coupure reshaped European ecosystems completely, creating faunas that were more similar to those of Asia, and marking the end of a unique European evolutionary experiment. Chapter 21. The world begins to cool. The Oligocene epoch, from 34 to 23 million years ago, marked the beginning of a long cooling trend that would eventually lead to the Ice Ages. This cooling was driven primarily by changes in Earth's geography and atmospheric composition. Antarctica, which had been warm and forested during the Eocene, became isolated as it separated from South America. This allowed the Antarctic circumpolar current to develop, a powerful ocean current that flows around the continent, isolating it from warmer waters. Without warm currents reaching its shores, Antarctica rapidly cooled. Snow that fell in winter no longer melted completely in summer. Year by year, the snow accumulated, compressing into ice. Within just a few 100,000 years, Antarctica was covered by ice sheets kilometers thick, ice that persists to this day. The formation of this ice had global consequences. Ice reflects sunlight back into space rather than absorbing it like dark ocean water or land. This increased the cooling effect, creating a feedback loop. Sea levels dropped as water became locked up in Antarctic ice, exposing coastal areas and land bridges. Ocean circulation patterns changed, affecting climates worldwide. Atmospheric carbon dioxide levels decreased, partly due to the weathering of rocks in mountain ranges that were rising during this time, such as the Himalayas and Alps. The cooling was not uniform or steady. There were periods of relative warmth interrupted by cooler phases, but the overall trend was clear. The greenhouse world of the Eocene was giving way to a cooler, more seasonal climate. Tropical forests retreated toward the equator. Temperate forests replaced them at middle latitudes. In some areas, particularly in the interiors of continents, forests gave way to more open woodlands and eventually grasslands. This environmental change drove evolutionary changes in animals and plants worldwide. Chapter 22. Saber-toothed beginnings. The evolution of saber-toothed predators represents one of the most remarkable examples of convergent evolution in the history of mammals. Saber teeth, elongated canine teeth used for delivering killing bites, evolved independently in several different mammal lineages over tens of millions of years. The first saber-toothed mammals appeared in the Oligocene around 30 million years ago. These early forms were not members of the cat family, but rather belonged to a group called nimravids, sometimes called false saber-toothed cats. Nimravids looked superficially similar to cats, but were actually a separate family of carnivores that evolved similar features independently. Species like Eusmelus had enormously elongated upper canine teeth, in some cases reaching lengths of 15 centimeters. These teeth were used to deliver precise, deep bites to the throat or belly of prey, severing major blood vessels and causing rapid death. The evolution of saber teeth was likely driven by changes in available prey. As herbivorous mammals grew larger and more robust, during the Oligocene and Miocene, predators needed more effective killing methods. A simple bite to the neck might not penetrate the thick hide and muscle of large prey. Saber teeth allowed predators to make deeper, more devastating wounds. However, these specialized teeth came with trade-offs. They were fragile and could break if the predator bit into bone. Saber-toothed predators had to be careful and precise in their attacks. True cats would later evolve saber teeth independently, producing famous species like Smilodon, the saber-toothed cat of the Ice Age. But the first experiments with this body plan occurred much earlier, showing how evolution repeatedly converges on effective solutions to similar problems. Chapter 23. The Miocene Mammals. The Miocene epoch, spanning from 23 to 5 million years ago, was perhaps the golden age of mammal diversity. This period saw mammals reach their peak in terms of species numbers and ecological variety. The climate during the early and middle Miocene was warmer than today, though cooler than the Eocene. Forests were still extensive, but grasslands were expanding, creating a mosaic of habitats. In Africa, the Miocene witnessed an explosion of ape diversity. At least 30 different species of apes lived in African forests during this time, occupying the ecological roles that monkeys fill today. These apes ranged from small fruit eaters to large terrestrial forms. Among them were the ancestors of modern gorillas, chimpanzees, and humans, though identifying which fossils belong to which lineage remains challenging. In Eurasia, enormous rhinoceroses grazed on grasslands. Dinotherium, the strange elephant with downward curving tusks, reached sizes exceeding modern elephants. Chalicotheres, bizarre relatives of horses with claws instead of hooves, browsed on leaves while standing upright on their hind legs. In the Americas, a different array of unique mammals thrived. South America remained isolated, home to giant ground sloths, glyptodonts, which were armored mammals the size of cars, and forests, racids, the terror birds. North America had its own distinctive fauna, including three-toed horses, pronghorns, camels, and oreodonts, which were sheep-like mammals that have no modern descendants. The oceans teemed with marine mammals. Whales had fully diversified into their modern groups. The largest shark ever to exist, Megalodon, patrolled the seas, reaching lengths of 18 meters. This diversity reflected the variety of habitats available and the relative stability of climate during much of the Miocene, allowing ecosystems to develop complexity. Chapter 24: Grasslands Expand. During the Middle and Late Miocene, from about 15 to 5 million years ago, grasslands underwent their greatest expansion, transforming entire continents and driving massive evolutionary changes. What had been primarily a habitat of Africa and parts of Asia spread to cover vast areas of North America, South America, and even parts of Europe. This expansion was driven by several factors working together. The climate continued its long-term cooling and drying trend. Continental interiors, far from oceans, became particularly dry. In these conditions, trees struggled while grasses thrived. Fire became more common in drier climates, and grasses, which recover quickly from burning, gained an advantage over woody plants. The expansion of grasslands fundamentally altered the evolutionary trajectory of many animal groups. Herbivores became larger as open plains could support vast herds in ways that forests could not. Horses evolved from small forest browsers into large plains runners, their teeth becoming taller and more complex to handle tough grass. Their feet evolved from having 3 or 4 toes to having a single toe with a large hoof, allowing faster running. Bovids, the family that includes antelopes, cattle, sheep, and goats, underwent explosive diversification in grassland habitats, evolving into dozens of different forms adapted to every variation of open habitat. Predators also changed. In forests, ambush hunting from cover is effective. On open plains, different strategies are necessary. Some predators, like cheetahs, evolved incredible speed to chase down prey in open terrain. Others, like lions, evolved sophisticated cooperative hunting strategies. Still others, like hyenas, became primarily scavengers, following herds and feeding on the weak and dying. The grassland expansion was not just a change in scenery, but a complete reorganization of terrestrial ecosystems that shaped the evolution of countless species, including our own ancestors. Chapter 25: The Messinian Salinity Crisis. Between 6 and 5.5 million years ago, one of the most dramatic events in recent geological history occurred. The Mediterranean Sea, that great body of water separating Europe from Africa, nearly dried up completely in an event called the Messinian Salinity Crisis. This extraordinary event happened because of changes in plate tectonics and sea level. The Mediterranean is almost completely enclosed by land, connected to the Atlantic Ocean only through the narrow Strait of Gibraltar. During the late Miocene, the African and European plates shifted, temporarily closing this strait. With no water entering from the Atlantic, and with evaporation exceeding the input from rivers, the Mediterranean began to dry up. Over thousands of years, sea level in the Mediterranean dropped by hundreds of meters. Eventually, much of the sea became a vast, salt-encrusted desert lying far below sea level, similar to Death Valley but on a continental scale. Only a few isolated hypersaline lakes remained in the deepest parts of the basin, with salt concentrations far higher than normal seawater. The environmental consequences were severe. Marine life in the Mediterranean was nearly completely wiped out. The surrounding lands experienced dramatic climate changes, becoming hotter and drier. Rivers that had flowed into the Mediterranean, including the Nile, carved deep canyons as they descended to the dried sea floor, canyons that would later fill with sediment when the sea returned. For animals living around the Mediterranean, the dry sea floor created new migration routes. Species could walk from Europe to Africa and vice versa across what had been sea bottom. This allowed mixing of previously separated faunas. The crisis ended about 5 million years ago when the Gibraltar Barrier was breached, possibly by an earthquake. Atlantic waters poured through, refilling the Mediterranean basin in what may have been the largest waterfall in Earth's history, a cataract that could have completely refilled the sea in just a few years. Chapter 26. The Pliocene Transition. The Pliocene epoch, from 5 to 2.5 million years ago, was a time of transition between the relatively warm Miocene and the ice ages that would follow. Climates continued to cool, though not steadily. There were warmer periods interrupted by cooler phases, a pattern that would become even more pronounced in the subsequent Pleistocene. Ice sheets began to expand and contract in the northern hemisphere, creating glacial and interglacial cycles. During glacial periods, ice covered large parts of North America and Eurasia. During interglacials, the ice retreated, though never as completely as in earlier epochs. Sea levels rose and fell in response to water being locked up in or released from ice sheets, alternately exposing and flooding coastal areas. The Pliocene was generally warmer than today, with global temperatures averaging 2 to 3 degrees Celsius higher. The Arctic had not yet developed its permanent ice cap, though Antarctica remained frozen. This warmer world featured forests extending further north than today, with trees growing well above the current Arctic Circle. Tropical forests were more extensive. Grasslands, however, continued to dominate in many regions, supporting diverse communities of grazing animals. During this epoch, many modern mammal genera appeared, making Pliocene faunas recognizable to modern eyes in a way that older faunas are not. Horses, camels, elephants, and big cats of the Pliocene looked quite similar to their modern descendants. However, there were also holdovers from earlier times. Giant ground sloths still roamed the Americas. Chalicotheres, those strange claw-footed ungulates, persisted in Africa and Asia. The Pliocene world was a mixture of the ancient and the modern, the last epoch before the great ice ages that would push many species to extinction and set the stage for human dominance. Chapter 27. Land bridges form. Throughout the Cenozoic era, the configuration of continents changed significantly, and these changes had profound effects on animal evolution and distribution. During the Pliocene, around 3 million years ago, one of the most significant land bridge formations occurred when North and South America connected through the Isthmus of Panama. Before this connection, South America had been an island continent for over 50 million years since the early Cenozoic. During this isolation, a unique fauna had evolved, including marsupials, xenarthrans, which are the group containing sloths, armadillos, and anteaters, and various unique ungulates found nowhere else. The continent had no placental carnivores except for the terror birds. North America had a very different fauna, including advanced placental mammals like horses, camels, bears, cats, and dogs. When the Isthmus of Panama formed, these two long separated faunas could suddenly interact. The result was the Great American Biotic Interchange, a massive migration of species in both directions. Initially, the exchange seemed balanced. North American species moved south, while South American species moved north. Ground sloths, glyptodonts, armadillos, and porcupines successfully colonized North America. Some, like ground sloths, reached as far as Alaska. However, over time, the exchange became asymmetrical. North American mammals proved more successful in South America than vice versa. Advanced predators like cats, dogs, and bears outcompeted or preyed upon many South American natives. More efficient herbivores like deer and horses displaced native grazers. Many uniquely South American mammals went extinct, unable to compete with the northern invaders. This pattern illustrates that evolutionary innovations developed in more competitive environments often prove superior when isolated populations are suddenly exposed to outside competition. The land bridge transformed the faunas of both continents, and set the stage for further changes during the coming ice ages. Chapter 28. The Great American Interchange. The Great American Biotic Interchange, beginning approximately 3 million years ago, was one of the most significant biogeographic events in recent Earth history, when the Isthmus of Panama formed, creating a continuous land connection between North and South America. Animals that had evolved in isolation for tens of millions of years suddenly encountered each other. The initial migrations were dramatic. From South America, ground sloths lumbered northward, eventually reaching Alaska and establishing populations across much of North America. These enormous herbivores, some weighing several tons, browsed on leaves and branches using their powerful claws. Glyptodonts, giant armored mammals resembling Volkswagen beetles with tails like spiked clubs, also moved north, though they did not spread as far. Porcupines, capybaras, and various marsupials, including opossums, made the journey successfully. From North America, the migrations were even more extensive. Members of the camel family moved south, eventually evolving into llamas, alpacas, guanacos, and vicuñas in South America, though camels themselves would later go extinct in their North American homeland. Horses, tapirs, deer, and peccaries all successfully established populations in South America. Most significantly, advanced carnivores moved south. Bears, cats, including ancestors of jaguars and pumas, dogs, weasels, and raccoons, invaded South America and transformed its ecosystems. These efficient predators quickly became dominant, replacing or outcompeting many native South American carnivores. The terror birds, which had ruled South America for millions of years, could not compete with these sophisticated mammalian predators and declined toward extinction. Native South American ungulates, which had evolved in the absence of advanced predators, were particularly vulnerable, and many went extinct. The interchange fundamentally reshaped the ecology of both continents, creating the distinctive faunas we see today, where jaguars hunt in Amazonian forests and opossums scavenge in North American suburbs. Chapter 29. Our ancestors stand upright. While the great mammals of the Pliocene spread across continents and evolved into new forms, in Africa, an event of profound significance was occurring. Our own ancestors were beginning to walk upright. The transition from four-legged movement to bipedalism, walking on two legs, is one of the defining characteristics of the human lineage. This change occurred gradually over millions of years, beginning perhaps as early as 7 million years ago. The earliest definitive bipedal hominins lived during the Pliocene, between 4 and 2 million years ago. Australopithecus afarensis, perhaps the most famous early hominin thanks to the skeleton known as Lucy, lived in East Africa between 3.8 and 3 million years ago. These creatures stood about 1 meter tall and had brains only slightly larger than chimpanzees, but they walked upright on two legs. Footprints preserved in volcanic ash at Letoli, Tanzania, show 3 individuals walking together 3.7 million years ago, providing direct evidence of bipedalism. The reasons for the evolution of bipedalism are still debated, but several factors likely contributed. Standing upright freed the hands for carrying food, tools, or infants. It allowed early hominins to see over tall grass in the increasingly open habitats of Africa. It reduced the amount of body surface exposed to the intense midday sun, helping with temperature regulation. It may have been more energy efficient for traveling long distances across open country. Whatever the reasons, this change set our ancestors on a unique evolutionary path. Bipedalism would later allow the evolution of larger brains, as changes in the skull, necessary for balancing the head atop an upright spine, created space for brain expansion. It would enable the development of tool use and eventually technology. The story of humanity begins here, on the African savannas of the Pliocene, with our ancestors taking their first upright steps. Chapter 30. The stage is set. By the end of the Pliocene, approximately 2.5 million years ago, the world had been transformed from the greenhouse planet of the Eocene into something approaching its modern configuration. Continents had reached their current positions. Antarctica and the Arctic were frozen, though the Arctic ice cap was still not as extensive as it would later become. Ocean currents had established their modern patterns. Grasslands covered vast areas of every continent, supporting diverse communities of large herbivores and their predators. The mammals that inhabited this world were largely recognizable as ancestors or relatives of modern species. Elephants, horses, cattle, deer, cats, dogs, and bears all existed in forms quite similar to those of today. However, they were generally larger than their modern descendants, and there were more species, greater diversity within each group. The stage was set for the Pleistocene epoch, the age of ice that would follow. Over the next 2 million years, climate would oscillate between glacial and interglacial periods, with ice sheets advancing and retreating in cycles lasting tens of thousands of years. These climatic swings would drive many large mammals to extinction, particularly in the northern hemisphere. But they would also create the conditions that would allow humans to evolve and spread. Our species, Homo sapiens, would emerge from Africa during the Pleistocene and would eventually dominate the planet in ways no other mammal had done before. The forgotten age after the dinosaurs had come full circle. It began with a catastrophe that wiped out the dominant animals of its time. It would end with another wave of extinctions, this time caused not by an asteroid, but by the actions of a single species descended from those small mammals that had survived the impact 64 million years earlier. The age of mammals was ending. The age of humans was beginning. And as you drift off to sleep, you can reflect on this incredible journey, from the fire that fell from the sky to the ancestors who stood upright and looked toward the future, wondering what would come next.